I think I'll dive into the nonlinear regime now. You will hear a lot more about how simulations are actually performed and probably more details of the extended projector theory. But today I think I will focus on a particular property of halos, basically a very general property, which is how they actually grow through mergers. So the basic idea here is dark matter. As we saw, there are these initial fluctuations, and they will go through the linear phase, and then they will collapse nonlinearly. And they don't really spontaneously just collapse at different points in space and then just sit there and accrete sort of dark matter particles. That's not the main way they grow. Instead, after a certain first generation of halos, they grow. One channel for them to grow is through merging with other halos. So merger is a very important basic mechanism for gaining mass for halos. So today, I think I'll just focus on number one here. If I get through it quickly, I'll talk about number two. But the idea here is just how fast, what is the rate of mergers of dark matter halos? And I'll also talk about, when we look at that in more detail, whether the merger rate actually depends on environment. So why do we care about mergers, other than the fact that halos seem to grow primarily through this mechanism in simulations? Well, I think another very important motivation is that we see mergers observationally. I'll show sort of three examples of mergers. Number one is these classical pictures of grand design spirals, which are obviously either about to merge. This is the M51, two galaxies, or this is the Antennae galaxy. It has probably merged, and you see these beautiful tidal tails. Usually we see these in simulations, hydrodynamical simulations, after the first passing. And so this is examples of mergers of two spiral galaxies, which are typically very gas-rich. But the part that you can't see, and we think it's there, are two very large, more diffuse dark matter halos that are first merging, and then the baryons inside come close, and then eventually everything will settle down. And this is believed to be the way that elliptical galaxies, at least the sort of run-of-the-mill elliptical galaxies, are formed through mergers of two spiral galaxies. So there are abundant examples of such systems in the universe, and this is a very large burst of star formation often accompanies such processes. A second example of mergers in observations, I will also point out that not only do spiral galaxies merge, there seems to be evidence that elliptical galaxies also merge. In some ways, we probably need them to merge in order to form these most massive ellipticals that we see typically residing at the center of clusters of galaxies, these so-called BCG, brightest cluster galaxies. These tended to have 10 or up to 10 L stars. So I think just two wimpy spiral galaxies merging, usually it doesn't get you up to such a high luminosities. You need subsequent mergers in order to grow these most massive galaxies. And here is an example of a rich cluster at redshift point 83. And here are HST images of pairs of red galaxies by Tran and Van Dakum et al. And the separation here is 40 kiloparsec. So we are probably witnessing, some could be chance pairs, although these authors have studied the velocity offsets, and they think these are candidates. for either future mergers or maybe mergers in process. Okay, so again, behind this, or what we can't see here, are the two very large dark matter halos hosting each of the elliptical galaxies that's also merging at the same time. And these mergers obviously typically are found in clusters because that's where most of the ellipticals reside. And also relevant for mergers is this very fascinating development in the mergers of supermassive black holes. And here is a beautiful example of two nuclei in the galaxy NGC 6240. And this is seen in Chandra. This is, I think, 5 to 8 keV, very hot emission surrounding two nuclei. The separation is approximately 1 kiloparsec. So the belief here is when two galaxies, when two dark matter halos come together and the centers of the galaxies come together, they will lose their orbital energy through dynamical friction. And if each galaxy has a central massive black hole, they will eventually form a binary. And if they could lose more energy through kicking of stars and so on, they could perhaps form a bound system. And then if you can lose even more energy and solve the final parsec problem, you can actually have the two black holes coalesce. And this is considered the primary source for gravitational radiation for the LISA upcoming satellite.
I have a question. Yeah. It's about the black hole. Is it possible, maybe it's a dummy question, possible that the black hole is composed of the material of the dark matter halo? Or the dark matter can induce or produce also black hole? Or?
Well, there's no way to dissipate dark energy, dark matter, unless you have some exotic form of way to do that. I think your question is whether the center could be a very concentrated clump of dark matter. Is that right? Yeah, I think the best studied example of supermassive black hole are not these, but the one at our galactic center. And I think people have ruled out various, because they can go to such a small scale to see the Kepler orbits of the orbiting stars. Although they aren't at the torsional radius yet, I think it's very hard. People have tried strange star clusters and so on. I think you can't completely rule them out, but I think black hole appears to be the most elegant candidate. Okay, so seeing mergers everywhere in the universe, then a very basic question we can ask is, we can go back to dark matter halos and ask how fast are they merging? Now, I believe Simon is going to go into much more detail about properties of individual halos, okay, such as its density profile, concentration, and various other quantities of individual dark matter halos. But for this lecture, I would like to concentrate on the dynamical process of mergers of dark matter halos. And it's kind of interesting that I think the properties or the number counts, mass function of dark matter halos, those have been studied quite well in the past 5 to 10 years. But to study mergers, since it's a two or n body process, you need a very large numerical simulation before we get the dynamical range to study mergers. For example, we would like to know for a given mass halo over a wide range of redshift, what's their distribution of their progenitors, their mass ratios, and so on. So we actually need to track not just a snapshot of an output from a simulation. We need to know who goes into what halo. We need this entire ancestry, this tree of halo mergers. And that made the calculation somewhat more complicated, and that's where large numerical simulation becomes extraordinarily powerful. So I'll describe some work I've done in the past 2 years with my graduate student, Ansi Fakhuri at Berkeley. And there we use the Millennium simulation, which you will hear more about later from Carlos and Simon. And I just want to briefly review the numbers that went into the Millennium. It has many, many particles, and the particle mass is approximately 10 to the 9th solar masses in a very large box. And I want to focus on the halos in this simulation. So they provide a halo catalog, and from the beginning of the simulation to the end, there are about 18 million halos. I think these have more than, I don't know, 25 particles or so, something like that. And out of these, there are, at today, redshift 0, there are 300,000 halos with masses about comparable to the Milky Way halo or above. This is a very rich statistic that we can use because you want to be able to resolve not just the halos today, but their smaller components earlier on. So now, given these halo catalogs, we actually need to construct these ancestral trees. So there are 46 outputs available for the halo catalog from redshift 6.2 to 0. And at the lowest redshift, the spacing is quite nice. The delta Z between outputs is about 0.02. So that gives us good enough time resolution to track the growth of halos. And here are some numbers, just to give you an idea of the numbers we have for studying to count to halo mergers. We have put this into sort of 10 to the 12th, 13th, and 14th solar mass bins. And these are the redshifts we use to determine the rates. So at redshift 0, we look at redshift 0 halos and their progenitors at 0.06. I mean, we've tested 0.02 versus 0.04, 0.06. We have some convergence tests in our paper about that. I won't go into the details here. And this is at 0.5, redshift 1, 2, and 3. And here shows NP is the number of progenitors a given descendant has at that earlier output. Okay, I just want to show that you may think the naive picture is 2 halos come together, form a bigger one. 2 halos come together, form a bigger one. Things are a little bit more complicated than that. First of all, since the time resolution is so good, there are many halos that actually had only one progenitor that's resolvable. Okay, its mass can be changing, but we can't attribute that to another resolved halo. And I'll talk a little bit more about this so-called diffuse accretion part later. Okay. So NP are the ones with just single progenitor, and NP equal to 2, and we have tens of thousands of these, which are sort of 2 halos coming together, forming a bigger one. And then there are actually a number of them where they have multiple progenitors that you can identify that have gone on to forming a later halo. Okay. So, and cluster scale, you tend to have many, many more of these multi-body mergers. And we decide we are just going to count that if there's more than 2 progenitors, we're going to count NP minus 1 as the number of mergers. That is to say, if you have a finer time resolution, probably these NP, you don't have 5 halos coming in simultaneously. Right? It's more likely during this time output, one came in, another came in, another came in. And we've tested this hypothesis. It seems to be fairly robust. So before I present the results, I want to just mention one complication that comes into this building this tree. Okay? And this is not unique to the Millennium simulation. It happens in any tree anybody wants to construct. Now, but what is special about the Millennium is that the halo catalogs we get are based on subhalos. So they run a code called the subfind, which identifies, you need to decide which particles belong to which halo. Okay, so they give a catalog of subhalos with their, based on the searching for bound cold dark matter particles to a given center, if you can identify that. Okay, So we have a catalog of subhalos, and the Millennium Tree does give us each subhalo. It tells us where those particles have gone into at a later time. Okay. Now, simulations are complicated. So you rarely have all the particles ending up in a unique descendant. Okay, often these particles, which at an earlier time residing in a subhalo, they may, 20% may go into something else, 80% may go into a bigger one. So the typical assumption is you just identify the halo at a later time with the largest fraction of particles as the descendant. You would like to identify a single descendant for a progenitor. You don't want to keep fragmentations, because presumably that happens fairly rarely, although you could have mass loss, but unlike asteroids, which can break into parts, we don't generally believe that dark matter halos can just fission into two components, because gravity is mostly attractive, obviously. So here we're showing one example. Now here comes the problem. We're showing an actual tree. There are many, many of these, and some trees are very, very big with many, many branches. We try to choose a simple one, from redshift 0.24 to redshift 0. And so this is about 10 to the 13. This is in units of 10 to the 10. So it's about a 10 to the 13 solar mass halo today, and we're tracking its history going backwards. And the black circle shows the friends of friends halo. So what we do is you have the subhalos, and then you can run a friends of friends linking algorithm to decide what is the actual main halo. And we have this from the Millennium simulation also. So the white circles indicate the subhalos residing in the main big halo. So you can see for the small ones, often one subhalo resides in the one friends of friends halo. But for bigger guys, it often has subclumps of subhalos along with the main subhalo. Okay, so this is the substructure that has been mentioned, and I think we'll hear more talks about this. Now the key here is when we go back in time, here you see nicely three things coming in together. Now, however, we highlight this yellow region where you see that at redshift 0.06, and also earlier on, this has a nice big halo consisting of 7 subhalos. But at a later time, this subhalo had gone out, and the algorithm identified this as a separate halo. Okay, we call these fragmentations.
But the friend-of-friend scheme is okay because some particles won't be bounded gravitationally.
So the subhalos include all the bound particles. Now the friends of friends mass, indeed, includes a subhalo mass and the unbound mass. And we actually tested the difference between the friends of friends mass and the sum of the subhalo mass. That moves you from bin to bin a little bit, but it's not that bad. So the difference is not that big. Okay, so what I'm trying to say here is this complication actually occurs in any other simulation, because most simulations don't go into finding subhalos first. They just run the friends of friends. Often they run the friends of friends linking algorithm on the dark matter particles themselves. But you also have this problem, just like I said, because you could have 80% going in here, 20% going in here. Now you need to make a decision about what to do with them. Okay, so I just want to mention, I won't go into the details here, that for this part, for example, there are at least 3 ways you can deal with these fragmentation events. And they are quite important for counting merger rates, but important only in the sense that it makes maybe we found 20% difference for most of the parameter range we studied. And we only found that out after we tried these different mechanisms. So the usual assumption that people don't say, okay, but that's what they do, is what we call snipping. So basically, like I said, if a fragmentation occurs, people generally assume this just goes into the biggest piece that contains, or the piece that contains the largest fraction of the original number of particles is called the descendant. Okay, so effectively they are snipping this link. And that's usually what you could do this. However, what may happen is, we are worried about this, because if you didn't do anything to the Millennium subhalo catalog, you would be constructing a tree based on this mechanism. Now the problem here is, as you saw in the animations, that the simulation output that you often see is you have subhalos coming in to the main halo, and then they go out of the virial radius and then come back in. Okay, so the problem is this could be a subhalo that's in process that has already gone through its first merger, but it's just gone out, and simulation happened to output the particles at that time, right? So, but then if you keep counting each of the passing, then you will be artificially inflating the merger rate.
Is that the case for the red object to the left? You have that red guy that merges and it doesn't come out? Or is that a different?
So that's the question, right? For this one, I don't remember. No, here you see it, right? Exactly. That's exactly the point. Right, so that's exactly the point. So they went out in and out in, and then it stayed merged. So you may want to just count the first time as the merger, and then you don't count the subsequent time, right? We want to sort of be careful with this. So anyway, so we explored two alternatives. One is what we call stitching. So instead of letting it snip, we just put it back in. So then when you're counting mergers, this will be one event, but this will no longer be a merger because the yellow one has been put back in. And we also try sort of the other extreme, saying, oh, maybe friends of friends was making a mistake here, linking artificially two things, so you could split it at an earlier redshift too. Okay. This gets fairly complicated, but we wanted to be careful. So at the end of the day, we decided what's called stitch 3 would be our sort of most neutral algorithm, and that is to say any fragmentation that came back in within 3 time steps, we just stitch it together because we think it's most likely a subhalo just flying around doing its many passings. So now I just want to show you our results based on the stitch 3 mechanism, stitch 3 algorithm for treating fragmentations. So what turned out was that what you can do first is, so the basic thing we want to count is, at a given redshift, we have the descendant halos in many mass spins labeled here, and this is at redshift 0. Okay? So we have galaxy size and up to cluster size halos. And we count its progenitors at an earlier redshift. And then we have 3 variables here. Redshift is 1, here is 0. And we can count the progenitor mass ratios. Okay, so when the mass ratio is very close to 1, it's a major merger. When it's very small, it's a minor merger. And we can count that as a function of the descendant halo mass. And here is the sort of raw number we got out of it. So it has a not very convenient unit. It's per volume per mass. And we divide by per unit redshift. I'll show per giga-year in a second. Okay. So what you're seeing here basically are 2 trends. Okay, there are many more minor mergers than major mergers, understandably. And their lower mass halos experience more mergers, but remember this is the total count, so this is higher just because there are more lower mass halos. So after but intriguingly, they all seem to follow some sort of power law here. So we thought it really makes more sense to calculate the mean mergers per halo, the average number of mergers a halo would experience. So we would like to divide this by the number density of the descendant halos per volume. And after we did that, so we called this B, and after we did B over little n, where n is the number density of halos, a remarkable thing happened. All these curves collapse onto each other. Okay, so meaning there is a roughly universal form or meaning there's a very weak mass dependence for merger rates. And so this is a very convenient, the y-axis, it's a very convenient dimensionless number. It is the mean number of mergers per halo per redshift. Or another way you can view this is the fraction of halos that's undergoing mergers for a given mass spin and a given mass ratio. Okay. And the red curves are the more massive ones, appear to be slightly higher here than the lower mass halos on average, but the difference is very small, maybe only a factor of 2 or so. So I can sum up the different mass ratios for the progenitors, and I can now, instead of plotting B over N, the merger rate as a function of minor versus major rate, major merger ratio, mass ratio, I can now plot the total number of mergers, or the sum over different ranges of progenitor mass ratios. Now, as a function now of the descendant mass, so this axis was showing up as different colors in the previous slide. So the fact that all these curves are very flat here is exactly reflecting the fact that they are all pretty, at a given mass ratio, they're all pretty similar, with the massive halo experiencing slightly higher rate of merger. So what you're seeing here is each curve down here is a range of Cassie, which is the progenitor mass ratio. So this is for mergers with mass ratio of within 1, 2, 3. So these are very major mergers of two comparable mass halos coming together. And as you've seen earlier, there are maybe more minor mergers than major mergers. But the weak mass dependence is very weak. And now you can actually read off the numbers here. That is to say, on average, a halo, regardless of its mass, experiences about 1 merger that's within a mass ratio of 1 to 10 per redshift. And they're up to 10 if the mass ratio is about 1 to 100, so these are fairly minor mergers, and there are fewer major mergers. So this is at redshift 0. Now we can study this for redshifts out to redshift 6, where we have the halo catalog. So now I will show the mergers as a function of redshift. Okay. So the x-axis now is redshift, and the different colors are still the major merger versus up to minor mergers. However, within each one, now we're showing the 3 mass spins, galaxies, groups, and clusters, and the fact that, and this is, the difference is about a factor of 2 here, and this is exactly the difference in the mass, the dependence on mass that you saw earlier. Okay. So the key feature of this plot is, again, if you count the mergers per halo per redshift bin, it's remarkably constant. It depends very weakly on redshift. So given these features, it allowed us to come up with a very simple fitting formula for the merger rate, for this dimensionless merger rate, which I'll show in a second. Now, often people like to calculate the merger rate per gigayear. Okay? So since per redshift, at lower redshift, contains much larger delta t. So when we divide, instead of a delta z, if we divide by delta t, then per gigayear, of course, the merger rates are rising with redshift. And here's a look back time, and here's the redshift on the same axis as here. So the merger rates per halo in terms of per gigayear does rise at earlier redshift. And here, these numbers are the rough power law approximation for, these are major mergers, minor mergers, and for each of the mass spins we had. And the power law comes out between 2 and 2.3, with a slight inflection here that it seems to be slowing, it's deviating from power law a little bit at late time. we're not sure if this is because lambda is kicking in or not. Okay. So this is the merger rate per gigayear. So now if we put everything together, so here you see, so these are some nice units now. If you are an observer, you want to know how many mergers there are per gigayear. You can see the numbers are between very few for the major merger to order 1 at redshift 0, but they grow up to between unity to 20 or 30 at higher redshifts. So this is the fitting form, sort of the universal function we came up with for this average merger rate per halo based on the Millennium simulation. And again, the 3 key variables are the descendant halo mass, that is, are you interested in the mergers of clusters or groups or galaxies at a given redshift? Okay. And alpha is very small, again, the weak mass dependence I have been pointing out, with a slightly higher rate at the cluster end. Kasi, again, is the mass ratio of the progenitors. Okay, so you saw earlier on the curves kind of look like that. So the power law is roughly -2. And at the major merger regime, there's a slight upturn, so we try to use another function just to capture that feature. So these 2 factors can account for the shape of the dependence on the progenitor mass ratio. And then you saw that the merger rate per redshift was very, very flat as a function of redshift. But in order to capture that slight change, rise in merger rate, we have a weak dependence. We use the linear growth function here. I'm not writing out the actual expression, but you can look up our paper for that. So now we have quantified the merger rates of halos in simulations. So I just want to say very briefly about how they are connected to actual galaxy mergers one can measure. Okay. So one important thing to note in our work is there we were just counting halo-halo mergers. Okay, so we are not, when we say we're looking at a cluster, we're looking at how it was put together, the dark matter components are put together. We're not talking about, say, the merger rates of galaxies inside of clusters. Those will require not only having the subhalos, but painting on baryons. And that was indeed what was done in Guo and White in 2008. Based on, so this work is based on the Millennium simulation with the galaxy catalog painted onto the dark matter halos. I think we'll hear more about that later. And there's some, I just want to highlight a few recent papers. Stewart and Hopkins, an upcoming paper, they use our halo merger rate, and then you can assume a halo occupation number to assign galaxies within the halo, and then you can assign a time scale for the merger. Then you can convert, you can link up how halo mergers are, you can relay halo mergers to galaxy mergers. And Kevin Bundy, who's here, also has a paper that hopefully will be posted to the web soon on how close pair counts, how you would use close pair of galaxies to infer, to actually measure merger rates. I just want to mention that one key difference between galaxy merger and halo merger is that for halo merger, you saw a very weak mass dependence, sort of power law time dependence per gigayear. The results from these studies for galaxy merger seem to indicate that when you paint galaxies, the mass dependence becomes much stronger, and the time dependence becomes somewhat weaker. I won't go into the details here, but one implication here, of course, is if the merger rates are not the same, then the mass growth of halos won't be the same, it's never the same as the stellar mass growth. And baryon physics, of course, comes in. So for small galaxies, star formation obviously is critically important. Now for massive galaxies, the growth may be dominated by mergers, but then you need to worry about when two dark matter halos merge, how their baryonic component will merge. And you usually, either in semi-analytic galaxy formation models, you need to assume a dynamical friction time, because galaxies will merge much later, because they're much more centrally concentrated. So that time scale, typically we use some sort of dynamical friction time scale. And I just want to highlight this paper by Boyle and Colchin, saying that the standard Chandrasekhar merger time may be too long. So this is another piece that one needs to pay attention to when one converts or when one relates these two rates. Okay, so that's about the global merger rate. So now we have this number as a function of mass and mass ratio and redshift over a wide range of masses, from 10 to the 12th to up to 10 to the 14th, actually 15th, from redshift 0 to 6. And for mass ratios, that was fairly hard to get, that we were able to get down to about 10 to the minus 3 mergers, just because the resolution is so good in the Millennium simulation. So now I would like to look in slightly more detail on, now you can ask, are there other variables that the merger rate depends on, in addition to these obvious variables? So an immediate thing we started looking at is environment. And Simon yesterday talked about the assembly bias, that how older halos, at a given mass, older halos appear to be more clustered. And that's a very intriguing result because, as he said, in the Preschecter model, it doesn't exist. It's completely environmental dependent if you use a particular window function for smoothing. Okay. So we thought we'll just go into the Millennium and then let's just look at these halos. We have so many of them. So we can quantify, for a given mass, we can quantify where they live. Okay, what kind of density environment do they live? So the idea is very simple. We have, for a given halo, we go to that halo, we sit at the center, and we can compute the mean density from all the particles centered at that halo within some radius. Okay. And we've tested these radii from, this is 7 megaparsec, we've tested at 5 or 3. You don't want to take too small radius because that won't be quite representative of the environment you're living in. But if you use 7 or 5 or 9, it doesn't make too much difference. So here is just a simple scatter plot of the mass of each halo and the average density within 7 megaparsec that it lives in, based on the Millennium catalog. So for example, if you look at Milky Way galaxies, it spans a wide range of environment. Some live in, so 1 here is delta equal to 0, so that's cosmic mean. So left to that, these are voids. So there are plenty of halos actually living in a overall underdense regions, and some of them live in the very overdense regions. Now, however, when you go to higher mass, for example, clusters here, you start to see all the points converging to one point, and that's very simple to understand. That's because clusters are very massive, so if you count the overdensity, including yourself, the halo mass itself starts to dominate the environment. Okay, so in fact, this line shows you what the overdensity would be if you, the halo, is the only thing in that region, and there's nothing outside. Okay, so for small halos, of course, it doesn't matter. But when you go to clusters, if you count your own mass, you're counting, you're just using your own mass to infer the environment. I mean, that's just one feature of using this variable. However, we thought that's not quite what we want, because we want to separate mass from environment. Okay, that's sort of one thing that should be clarified. Often, people say loosely that clusters, they use actually clusters versus galaxies as environment, especially in observations. But here we're being a little more quantitative. Okay, we would like to say, I think we have more information. That is to say, for a given halo mass, you can actually calculate whether their surrounding material outside of the halo mass is more overdense or underdense. Okay, so that leads me to the two panels on the right. That is to say, you can calculate things by taking out your mass, the central mass itself. So you're hoping to disentangle the halo mass from this environmental variable. So when we carve out the central 2 megaparsec region for every halo, there's still residual memory of the clusters because some of these clusters are huge. They're reaching 10 to the 15 solar masses. So then we tried another recipe, which is, let's just take out the FOF mass of the central. Instead of just doing a fixed radius, we just take out the FOF mass of the central halo. So we are very cleanly calculating the surrounding region outside of the halo. And now you see that we are able to somewhat explore the environment for clusters too. Okay. So naturally, clusters tend to live in somewhat more dense regions. You find very few clusters in voids. Okay. But the dynamic range, again, for the lower mass halos, in terms of the environmental variable, is quite wide. So this allows us to, now we can ask a finer question here. I show you the global average rate, which is integrating over all the environments. Now we can go into each environmental bin and ask, is there any dependence of merger rate on delta? And I'll use F7 minus FOF for the rest of the talk. And here's our main result. For the merger rate, but as a function of 7 minus FOF, our environmental variable. And this is at 4 redshifts, 0.5, 1, and 2. Because we're now looking at environmental bins, the statistics become pretty ratty at higher redshift. So we stop right here. And the y-axis for the top panel plots the ratio of the merger rate of a given mass halos inside of the environmental bin to the global rate I showed you earlier, the first part of the talk. So here, different colors are the different mass spin halos. So red are clusters, blue are Milky Way sized halos. Again, overall, the mass dependence is very weak. This is a message that comes over and over again. Okay, the merger rate doesn't really care about the descendant halo mass itself. But within each mass spin, you see that denser regions, here is up to 10 for these smaller halos, experience higher rate of merger compared to galaxies or halos in the voids. And the difference can be about a factor of 2 from here to there. And this trend seems to persist over the entire redshift range we had statistics for. So we're able now to introduce yet another factor to our merger rate. If you ever care about the environmental dependence, there's a simple fit to this tilt as a function of delta. I won't quote it here, but we have a formula for that. So one can also ask, since in denser environments, it appears that halos are experiencing higher merger rates, then we can look, say, at a given halo. Okay, so that was just based on many, many halo statistics. Now we can actually go into a given halo and go backward in time and ask the contribution to its final mass from various types of processes. Okay, so you can ask, what is the fraction of a halo's final mass that's gained through a major merger in its history? Okay. And the major merger is defined at the time of the merger. So say if this halo, today's halo at redshift 3 experienced a major merger, we are referring to its mass at redshift 3 and a progenitor that came in within a factor of 1 to 3 here at that time. Okay, that's different from counting a merger ratio relative to today's number, just for those of you who care about the details. So again, I'm plotting now, so this is the corollary of the merger rate I showed earlier, but here is the mass fraction for a given halo that's gained through major merger in its history as a function of environment again. Okay. So you see this positive trend here again that in denser environments, for a given halo mass spin, okay, each of the color curve is a mass spin for the final halo mass. But again, there's very, very weak dependence there. But the general trend is that for a given mass, in the denser regions, a higher fraction of the halo's final mass is gained via major mergers. Now, here comes an important piece, which is the resolvable halos do not contribute to 100% of the halo's final mass, as I mentioned earlier. There's either unresolved halo or truly actually diffuse, tidally lost dark matter particles that contribute significantly to the final mass of a halo. Now, we are not able to tell which is which unless we have finer resolution simulations to compare with. That is to say, what we call this diffuse component, which we just take a ratio of anything that's coming in that's less than 1/40th the mass of the main halo, we call it diffuse. And this number actually is decided by the Milky Way size halos, which are the least resolved halos. And when you take 40th of a Milky Way halo mass, you have subhalos that contain only about 10 to 20 particles. So we don't trust anything below that. So this is the resolution, really, of the Millennium simulation for tracking mergers. So we call it anything, but to be consistent, for cluster mass, we also use the same mass ratio so that we can be fair. Okay. So anyway, if we looked at how this diffuse component, accretion, depends on the environment, very intriguingly, it has the opposite trend. That is, in denser regions, you get much more contribution, relatively, from major mergers or other kind of mergers than from this component we can't resolve. Okay. Now, the key message here is merger rates are just counting how halos come together to grow. Okay. But when you count halo mass growth, one contribution comes from mergers, and there is this non-negligible component from the diffuse accretion. Now, since these two have opposite trend, you need to sum up both in order to study halo's mass growth as a function of environment. So I will show the last slide here, which will put this together. Okay, so here comes the sort of the question you can ask is, okay, we found that merger rates are larger in denser regions, which seems to make sense. You got more stuff together, maybe things are merging. However, one implication of this would be, if you sit at redshift 0, for example, you look at the halos, since the halos in denser environments experience higher merger rates, you would expect them to have been formed more recently. Okay, so halos in more recently, meaning they're younger. So one implication, if you just use the top plot based on mergers, is that if mergers were the only way to grow halo mass, then the younger halos would reside in denser regions, which is exactly opposite to the assembly bias Simon talked about yesterday. Okay. So the way to resolve these two the opposite trend, is to note that the diffuse accretion, if you read the y-axis, there's a huge amount of a fraction of a final halo's mass, from 40 to 55, 60%, that's coming from this resolved component. And since this part has the opposite dependence, when you add up the two, and when you look at a halo's formation redshift, it comes out consistently. That is to say, okay, before I show the redshift dependence, formation redshift dependence, I just want to show one more thing here, which I forgot, which is you can ask, instead of the final halo's mass, where it's coming from, you can ask, what about the reservoir outside of a halo? Okay, whether that has any environmental dependence, because it's the reservoir of stuff outside of the halo that's feeding the growth of halos. So this plot shows, again, as a function of our environmental variable, the fraction of the mass in a 7 megaparsec sphere outside of the halo itself. You can look at the mass there and what fraction of that mass resides in resolvable halos versus diffuse component. Okay, again, you see this very clear trend that in denser regions, for a given mass, there is more material in halos than in diffuse accretion. So presumably, not all of this stuff is falling onto the central halo all very rapidly, but this is the reservoir of the growth of halos. Okay, so the same trend carries over to the surrounding material. So now I just want to show you our final result for the formation redshift. By this, we define this as sort of the standard definition in the literature, is you look at the halo at redshift 0, you follow its mass accretion history, and you can identify the redshift at which it acquired half of its mass. And that's usually tagged as the formation redshift. People have explored different kind of formation redshift definitions, but they are fairly similar. Okay, so the y-axis now shows the formation redshift for all the Millennium halos we have data for as a function of density. And just for comparison, I'm showing delta 7 versus 7 minus FOF. But the right panel I consider our main result, and for different mass bins. Okay, so first of all, the trend, the dependence on mass is very well known. That is to say, today's clusters are formed much more recently than today's galaxies. This is just a feature of a lambda CDM hierarchical structure formation. So clusters, the median formation redshift is about 0.65. And there is a very weak dependence on environment. And I think you saw this yesterday. Simon uses the bias, which is a statistical measure of how the clustering of halos are relative to the underlying density. The difference here is we're not using bias, but we're using the density locally, which we can attach to each halo. Okay? But presumably there is somewhat of a mapping between a denser environment and a more clustered halo, the higher it be. So the key difference here is when you go to the galaxy bin, you see now, right, the earlier forming halos at redshift about 1.4, the older halos, that is to say, they live in denser environments. Okay. So again, this is opposite to what you would infer from the merger rate alone. As I just said, higher merger rate would have implied a younger halo in denser environments, but because of the diffuse accretion part, it makes the two consistent. Okay, and then in the voids, you can see the redshift dropping. Now, just to close, and I'll continue in the next lecture. Now, we have an interesting two opposite trends here confronting any kind of analytical model you would like to build. For example, I think it would be very interesting to introduce environmental dependence into the extended pressure excursion set model. Okay, in its basic form, you saw that it's environmentally independent, meaning everything should have been flat here. Okay, but for now, the question is: are we gonna try to massage it to produce the positive correlation of merger rate with the environmental density, or sort of the somewhat opposite trend that older halos live in denser environments? Okay, they actually go in two opposite directions. And since EPS doesn't quite treat diffuse accretion or anything, it's a very simple recipe, I think it would be interesting to think a little more about that. So to summarize, we've measured the global halo merger rates from the Millennium simulation as a function of the halo mass and progenitor mass ratio and redshift. Okay, and it's very simple if you write this in terms of a rate per unit redshift. It depends very weakly on the mass and the redshift, and it has a sort of a power law, -2 dependence on the mass ratio. Now, if you write this as a per gigayear, it increases as 1 plus z to roughly the second power. But if you examine in more detail how the merger rates depend on halo environment, we found higher merger rates in denser regions. But since halos gain mass by both mergers and this diffuse accretion, and we found lower accretion rates in denser regions, the two combine to give a higher formation rate redshift, that is older halos in denser regions. Okay, thank you.